Welcome. Thanks for taking the time out of your busy schedules to come to the show. My name is Martin Van Ryswyk. I run engineering for DataStax, engineering and support, building all those things that Billy talked about in the keynote. And this is really awesome to see so many people packed in here to the meaty technical track to find out how data pipelining and the SMAC stack and all this kind of stuff works. It might be the busiest room we have as I was looking around the other ones, so it's really nice to see a lot of other techies. We spend a lot of time and effort at DataStax building and testing and making about 50 different projects work together and integrated so that you don't have to. I think you're going to hear today about how to go about using that in innovative and interesting ways by combining some other technologies to solve some great problems. I was hopefully going to have the agenda up here. There we go. There's the agenda of some of the speakers you're going to hear talking on this subject. Just a show of hands, how many people are already trying to do this and you're trying to find out more, some interesting tips? So, okay, a little fair more. How many are not doing it at all but think it's interesting and you just want to see if it's something to try? Right, great. So more tire kickers and interested in kind of getting the 101 version of it than the experts. It should be interesting. So I'm going to get out of the way and hand it over to the team who is going to hopefully answer those questions for you and give you some insights. So our first speaker today is Simon Ambridge. And Simon, come on up and I'll hand it off to you.
Thank you very much. Cheers, Martin. So good morning, everybody. Hello and welcome to the DataStax European Summit 2016. And in particular, thank you for coming to this track, being immediately decisive with DataStax Enterprise and Spark. So my name's Simon Ambridge. I'm going to be... beg your pardon. I'm going to be giving a talk today on, in fact, if we can go back to the first slide. There we go. An introduction to building agile, flexible, and scalable big data applications using DataStax Enterprise and Spark. So what I'll be giving is an introduction really to some approaches to architecting solutions for different types of big data pipelining use cases. And really I'll be setting the scene for some of the speakers that are going to follow after me today who are going to describe their experience, their use cases, and the approaches they've taken to solving their analytic solutions with DataStax Enterprise and Spark. So a little bit about me. My prior career before joining DataStax about 1.5 years ago has been pretty much exclusive with Oracle technologies. Started out as a DBA, Oracle version 5, so that was quite a while ago. Latterly as solutions architect with eBusiness Suite and Hyperion and Exadata and Exalytics Cloud, those kind of things. But I'm now a solutions engineer working for DataStax based in the UK. I've been with DataStax about 1.5 years, and it's nice now to be able to build the kind of solutions with DataStax that I wasn't able to build with my previous technology that I was working with. So, introduction to data pipelines. So, for the purposes of today's talk, I'm going to divide data pipelines up into two types, really. Effectively, one is going to be dealing with massive, large data sets, static data pipelines, and we're going to compare that with how you would build a solution to support real-time analytics streaming data. So massive data pipelines, these are typically things which are an element of research, so things like genomics data, clinical trial data, demographics. These could be terabyte and petabyte scale data sets, so we need an architecture that's capable of supporting that. And these are typically repetitive, iterative processes, analyzing data to come up with the conclusions that are needed from that data. We compare that with real-time streaming analytics. These are typically things associated with industrialized or commercialized processes. These are things like sensors, so wind turbines, power stations, vehicle automation, telematics, but again also transactional data, market tick data, and real-time personalization, presenting shoppers with offers targeted to their buying and spending patterns in real time. So, static data sets, we'll look at them first. So this diagram serves to represent what a traditional static data modeling process might involve. You have some data. It could be a very large amount of data. And ideally, if you have machinery that's capable of reading all this data and at one point you read it in, this typically happens on maybe one or two large machines, often a scripted process, shell scripts, which you tweak and then debug and then rerun, often from the top. So you take your data, you sample it, you might read it into a relational database or something, build out a schema, and then do some modeling on that data, and then ultimately get to the point where you're doing some reporting and hopefully deriving some meaningful analysis, and then you share that data with your consumers. And ideally that would be shared, for example, via some sort of web page, but in the worst possible case, you'd be sticking a spreadsheet in an email and then sending it out to people to review. They look at that data, they might not like your conclusions, or they might want you to tweak something or change something, so you go back to the beginning of the process, and again, it's a very iterative, slow cycle. That's not only the main problem. Probably the main problem is the fact that as these volumes of data get bigger and bigger, you're running up against some limitations on the machinery that you want to perform that analysis. There are finite limitations on the amount of CPU and memory that you can accommodate in a machine. And pretty soon you reach those limits and you're faced with a situation where you can no longer sample the data in its entirety, and you have to take subsets of the data and try and derive an analysis of that, and then try and bring those individual sub-analyses together in some meaningful way. So it's really far from ideal. And simplistically put, small data sets you can get in small servers, but as your data sets get bigger, ultimately you're going to get to the point where your hardware is no longer capable of reading those massive data sets in one go. And we've all heard about big data. Data really is getting big. The volumes of data are getting bigger. The number of the data sources is exploding. We're getting data from, everyone's talking about IoT. Everything is now something that sends data. And that data is arriving faster and faster, and there's just more of it. So ultimately, you come to the point where scaling up no longer is practical, and you're even maybe in a situation where the analyses you're doing on a data set has now become out of date because the data that you're analyzing has been replaced, and you're not able to come up with any analysis in a timely fashion. So what we need to solve this problem is we need some sort of scalable infrastructure, and ideally using distributed technologies to spread that processing and analytical load over as many machines as possible, ideally low-cost machines, perhaps cloud instances. And because we're putting smaller data sets to be analyzed into individual nodes within that cluster, we can probably perform faster processing on it because we're dealing with smaller chunks of data. And if we're processing that data faster, the chances are we can also introduce more complex processing than we would have been able to using some large monolithic machine. Another benefit, of course, of a distributed technology is that you take away the single point of failure. However, we understand that building a distributed data processing framework can be a complex task if you're starting out from scratch. What components do I need? How do I bring those components together? And how do I build a data pipeline from those components? It needs to be scalable. It needs to be able to do fast processing. So by default, we're probably talking about processing that data in memory. Ideally, we want to be able to replicate that data for resiliency as well, so that it's copied to more than one place. So a resilient, replicated persistence layer would be nice. And if we can support both batch and real-time streaming analytic modes, that would be great. So not just lifting data out and running processes of jobs against that data, but also being able to support streaming data with the same technology. And ideally, in this particular context of the static data analysis, it would be nice if you were able to run some ad hoc queries. So it would be nice if it was a flexible, interactive approach to data analysis. Now, in this situation, DataStax really can be your friend because we've taken the two major building blocks of that kind of technology, that kind of architecture, which is Cassandra and Spark, and we bring them together, but we don't just bring them together so they sit side by side. As we'll see in a couple of slides' time, we integrate those products very tightly so they bring a lot of efficiencies and reduction in latency to your architecture. And so I like to think of this as Cassandra Man with his faithful companion, Sparky the Wonder Dog, coming to the rescue. And I hope that's not the best quote of the day. So just a very quick look then. I mean, I'm sure we pretty all know what Cassandra is. It's a very, very fast database technology. It's extremely resilient. It fundamentally supports multi-data center geo-replication of data. We don't talk about high availability. It's not an active and a passive data center or a primary and secondary. Every data center in a Cassandra cluster is active. So we have continuous availability. And similarly, you can survive the loss of a node or a rack or even an entire data center without losing access to your data. So we're talking about disaster avoidance, not disaster recovery. The great thing about Cassandra is it scales in a linear fashion. So if you want 25% more computing power, you just add 25% more nodes. If you want 50% more storage, you add 50% more nodes. And also it's very easy to operate. People have described it as the most boring database technology they've ever implemented because it requires so little oversight and administration. And of course, the enterprise Cassandra platform is only available from DataStax, who are the commercial sponsors of the Apache Cassandra project. A quick word about Spark for those of you who are, anybody familiar with Spark? Ever see a show of hands of people who've got some familiarity with Spark? Okay, that's a good number. So you'll be familiar with the fact that fundamentally it's a distributed, in-memory processing analytical engine. It distributes the load over a number of nodes and processes that analysis in memory. It supports both batch and streaming analytic modes. It's very fast. It's typically 10 to 100 times faster than comparable jobs written in Hadoop MapReduce. And it's it offers some very rich Scala, Java, and Python APIs. So if you're familiar with those languages, you'll feel very much at home. Just to give you an indication of how fast Spark really is, the Dayton Gray benchmark contest is a test of how fast a system can sort 100 terabytes of data, which is 1 trillion records. The previous world record was held by a MapReduce cluster of 2,100 nodes. As you can see, it completed it in 72 minutes. And in 2014, Spark completed the same test on 206 EC2 nodes in 23 minutes. So it was 3 times quicker with 10 times fewer machines. So much less infrastructure involved and a much higher degree of much higher level of performance. The way that we integrate Spark and Cassandra together within DataStax Enterprise, within our platform, within our technology stack, you could have a cluster of Cassandra machines and a cluster of Spark machines, and they could move data between them. And of course, that would work perfectly well. You could also stream data into Spark and then persist it into Cassandra. But that movement between those two clusters of machines has to happen across a network, and that at best is going to take milliseconds. And we have customers in the online advertising space who have SLAs, very strict SLAs, where they have to respond within 75 milliseconds, for example. And if 20 milliseconds of that is spent moving data about, you've already lost a third of your SLA just moving data around. The DataStax integration of Cassandra and Spark, we co-locate the JVMs for Spark and Cassandra together on the same nodes. So that means that the data is moving just between the JVMs, and that reduces the transfer time, the latency, down to microseconds instead of milliseconds. So you're talking at least an order of magnitude improvement in performance of the transfer time. Another benefit of our integration is that these Spark JVMs, these Spark nodes, they're data aware, data locality aware. So when they lift data out of the Cassandra database, the Spark nodes lift the data from their corresponding node intelligently. Excuse me. So, getting back to the data pipeline element, so for this kind of iterative data science process, we need something that's ideally auditable. Now, data science is no different from any other science. You need to be able to have your analyses and your conclusions peer-reviewed. So you need something that's auditable, something that's easily shareable with your colleagues. Ideally something that involves some inherent documentation along with your working so that people can see why you came to the particular conclusions you used. Something, again, that's suitable for version control, so something that's text-based would be nice. And a tool that's ideally as collaborative and accessible as possible, so not something that's a chunky piece of software that you install on a client PC, but something that's web-based, browser-based, something that's easily accessible. And the solution for this problem becoming increasingly popular is the concept of notebooks. If you're familiar with notebooks, there are three main candidates at the moment. There's Apache Zeppelin, there's a Spark notebook from a company called DataFellas, and also Jupyter. And my colleague Duhai will be providing a demonstration of Apache Zeppelin a little later in the day. He's a committer to that project. But what they do, because they're web-based, they're very flexible, they're very interactive, and they allow you to drive your data analysis from the browser. And they're very interactive as well. You can go back and just change the workings of a particular step and then proceed from that step. You don't need to run things from the beginning because everything's running and being held in memory. So here's an example of a screenshot taken from a genomics research platform, actually. This work, as you can see, it's just a browser page. You get some controls across the top, and you have the concept of cells. Cells can include calculations, Scala code, Java code, Python code, whatever. And here we see an example where we built an RDD from another RDD by applying a Scala filter. And then in the next cell, we then do a count, and we get 1.2 million records. And if we didn't like that number, we could go back and just tweak that filter statement and run it again and then see what the answer was. So this is a much more interactive and flexible process than just writing scripts and running the scripts and debugging them running from the top all the time. So a typical architecture for this kind of process might be starting out with an optimized storage format. Something like Parquet is a very popular candidate for this. Parquet is a very efficient means of storing data. It's a columnar storage model. It's very efficient at compression and storage because you can apply different compression algorithms to different columns within your data. We need a distributed in-memory analytic engine, and obviously Spark is a great candidate for that. We're going to look at how notebooks are very, very flexible, interactive, and they allow you to do your analysis from your browser. You want to be able to save your data into a persistent data store like Cassandra. And ultimately, if you want to build some web services that allow other levels of access to your data, then Akka is a great candidate for that. For those who haven't looked at Akka, it's a highly distributed, highly concurrent web-based services or microservices-based environment for building web applications. And here's a real-life example. This is an agile data science toolkit. It comes from a company called DataFellas, again, the guys that wrote the Spark notebook. And they deal a lot of bioinformatics. This particular use case is genome research, so they're using the ADAM data sets. This is a set of libraries and standards for working with genomic data, but it's in Parquet format. They read it into a container, a Docker container, and they use the Spark notebook to drive their analysis and ultimately save it to Cassandra and make it available. Now, this particular workflow would be read the source data into your notebook. You do whatever you want to do with it. You can then run your Scala, whatever, to save it to Cassandra and make it available externally. But their vision and their reality is that this allows them to scale out using as many containers as they need to be able to scale to accommodate the volumes of the data they need up to petabyte scale. And using container deployment and management tools like Mesos and Kubernetes, they can effectively drive this kind of analysis and deployment, this very simple scaling out approach. They can drive that from their desktop. So we see that we go from a situation where we were doing a lot of repetitive, iterative phases for our data analysis. And this has now become a much more interactive and flexible process where we read the data in, we scale out to as much infrastructure as we need to support that volume of data, and then we make that data easily accessible and shareable by our peers. So that's static data sets. Moving on now to real-time data sets. So in a highly connected world, businesses need to be able to react to customers faster and with more accuracy. What this means is, for example, if you're an online retail website, you have customers who are browsing through your website. And if you can analyze in real time the sort of things they're looking at and the sort of things they're buying, you can give them offers in real time based on those browsing and buying patterns and buying history, which means you're much more likely to get a sale from that particular customer. So obviously this brings tremendous commercial advantages for online businesses. In the same way, businesses want to be able to reduce business risk by understanding exactly what it is that their market wants. You know, what particular demographics like which particular products, or what particular age groups, for example, so that you can specifically target products based on a thorough understanding of your target market. Marketing budgets can typically be hundreds of millions of dollars, so if you're spending that kind of money, you want to ensure that you're spending that money where you know it's going to be most effective, so that you're targeting exactly the people and the products you need. And I mean, also, of course, with things like plant and machinery, and bioinformatics, wearable technology, all these kind of IoT use cases, you can improve efficiency of machinery, for example. And in fact, the British Gas use case is a great example where they're using in their connected homes, their Hive project. They've got sensors in the domestic boilers, and they're monitoring the performance of those components of those domestic heating units, and they can proactively and predictably predict when those components are likely to fail, and have engineers visit the unit to replace those before they actually fail. And interestingly, for many companies, many organizations, for them, the definition of real-time data is data that's changing at sub-second intervals. So for these sort of situations and these sort of use cases, analyzing it every 5 seconds or every 2 seconds just isn't quick enough. It has to be analyzed in real time, which means being able to react to that data as it's coming in at sub-second intervals. So the problems we're trying to solve, we want to be able to capture, prepare, and process this streaming data, this data that's arriving at high velocity from a number of sources. And we know that we can't use traditional batch processing because it's not going to be running at the speed of now. We need to be able to analyze this data in real time. And this is going to give us immediate insight and tremendous commercial and engineering opportunities. Again, we've already mentioned the typical examples of streaming analytics, things like sensor data, transactional data, so everything from cash registers to credit card payments to market tick data. User experience, we're talking about targeting, again, offers for online shopping, for example, and social media. Social media is a rich vein of information there for businesses, looking at what people are saying about your products and understanding, is it a particular area of the country that's complaining about this, or is it a particular age group, or whatever. So when we think about streams, for me a stream suggests a gentle babbling brook meandering through a quiet leafy glade. But for many people, in fact, that data is arriving at much more of a problem level than that. They're talking about torrents of data, and for some people, they're even talking about tidal waves. Netflix, for example, they ingest petabytes of data per day. And this is over 1 trillion transactions a day, more than 10 million transactions per second being managed and processed on DSE. So for a streaming analytics architecture, what do we need? We need something that can perform those analytics. They can do it in real time and able to scale to support the growth of that processing demand. And we're increasingly seeing a technology stack which doesn't comprise just Spark and Cassandra, but also comprises Kafka. And Kafka, like Spark and Cassandra, is a highly scalable technology. It's highly distributed, and it's resilient. Kafka works by decoupling producers and consumers of data in a data pipeline, and my colleague Patrick McFadden recently used a great analogy. He said, imagine customers in a restaurant and imagine cooks. If the customers are just banging on the door of the kitchen saying, here's my order, the cooks don't know what order the orders came in and who to serve first, whatever. What you need is a broker between the customers and the cooks. And so we introduce a waiter. The waiter takes the orders from the customers and gives them to the cooks in the order in which they were received, and ensures that they are processed in the order in which they were received. And if you have too many customers, you just add more waiters. And if you've got more customers and waiters and you have cooks and the cooks are overloaded, you add more cooks. So this is really how you scale out both your Kafka cluster and your streaming processors that are consuming the data from that Kafka cluster. So say, for example, we have a weather station, and the weather station is sending sensor data for both rainfall and temperature. And perhaps we've got more temperature readings than we have rainfall readings, so we divide them up into topics, into separate topics. And then we have dedicated Spark consumers which consume that data from those topics. Kafka at a very low level allows you to parallelize your processing or your data feed by using partitions. And partitions could be dedicated to certain types of for example, all the temperature sensors beginning with the letter A might go in partition 0, all those beginning with B might go in partition 1, etc. Or you can have Kafka round robin through the partitions to spread the load that way. So as you get more signals, you can add more partitions to distribute the load. You can also add more brokers, so you can have additional Kafka servers running on other machines to spread the load and distribute the load in that way and scale out as you need. It's highly resilient because as the messages are received by Kafka, they're put into this ordered log and they're each assigned a unique offset so that the consumers are responsible for tracking their position as they consume the data from that log. And if a consumer fails, it would then resume from the point where it stopped consuming. So again, in that method of architecting is very resilient. Which leads us to a reference architecture which looks pretty much like this. Excuse me. So we have a set of sensors, and those sensors are sending signals. That data is being aggregated again by some form of web service. Again, Akka would be an ideal solution for that, some sort of microservices, a resilient distributed web architecture. And that feeds those signals to a Kafka cluster made up of one or more brokers, and those brokers are then responsible for allowing that data to be consumed by one or more Spark consumers. The Spark consumers then do whatever processing they want, and then they can then persist that data into the Cassandra database. This allows us to then introduce our real-time analytics. While that data is in memory, as it's being consumed by the Spark streaming processes, we can introduce our real-time analytic processing. So, for example, we can be monitoring equipment and looking for patterns of, or warning signs and reacting. We can take actionable insight. We can potentially detect fraudulent transactions or decide to sell stock based on a stock value, and personalization, presenting shoppers with the offers that they would be likely to respond to. Once that data is in Cassandra, we're then able to make that data available for external consumption, things like dashboards and other web applications that might want to read and write data into that cluster. And we see here, for example, that the data is being read in by the Spark consumers into an analytics data center, which can then replicate that data over to an OLTP data center. Now, touching upon that, one of the great features about Apache Cassandra is its multi-data center replication capability. This is a fundamental feature of Cassandra. You write data into one data center and it's automatically replicated over to a remote data center. So this gives us great resilience and it gives us great geolocation. It can bring the data closer to your users. We can also use that to good effect within DataStax Enterprise. We can use it for workload separation, so we can have an OLTP cluster, OLTP data center of Cassandra nodes, and we can have an analytics data center of Spark and Cassandra nodes. We don't want to impact the performance of our OLTP data center by running analytics on it, so we can separate it out. So as the data comes into our analytics data center, it can be, examined, analyzed, actioned, but it can also be replicated over to our OLTP data center. And that gives us a reference architecture, something like this. Supposing you are a electricity company and you have a number of sensors on a domestic electricity meter. All those signals are being fed in, aggregated, run through Kafka Cube, through Spark streaming, and being fed into an analytics data center, streamed in at high velocity. That data, as it arrives in that analytics data center, could be processed, real-time analysis and batch analysis if required as well. And it can also be then replicated to our OLTP data center so that users can come in on a web interface, for example, and they can watch their electricity consumption in real time. Another example might be biomedical monitoring, the ability to have those biomedical devices being monitored in real time, sending alerts if there's an exception condition or a patient's unwell. But doctors can also analyze or view that data, probably on a machine that goes ping, via the data that's held in the OLTP data center. So this is a really key benefit of using the DataStax Enterprise architecture, this workload separation, the ability to separate out OLTP from analytics. So, in summary, really, we've got two different types of data pipelines, but they've got a lot of similar requirements. A lot of things are common to both cases. In both cases, we want a scalable, distributed technology. We want something that allows us to save data into a reliable, persistent, resilient, distributed data store. And in the case of the static data pipelines, we want a nice, flexible, interactive method of analyzing that data. Now, we've talked today about Spark, Akka, Cassandra, and Kafka. And these are four of the 5 components that make up the SMAC stack. If you've heard of the SMAC stack, the M stands for Mesos. But in the use cases that I've described, in the architectures that I've described, we've looked at how you can build out data pipeline architectures using Spark, Akka, Cassandra, and Kafka. So I hope that was interesting. I can take it. Well, I think we're having a question and answer session later. But I think we're a bit ahead of time, so perhaps we can take some questions now if anybody wants to.
Can you hear me? Okay, now it's working. My name is Maciek from AutoCloud. We actually, just to set the scene, we're using DSC and Spark in production for almost 2 years now, so I'm a big fan.
Okay, good to hear.
But just yeah, I am really a big fan. But the question I have to you, mentioned somewhere along the slides about 75 millisecond SLAs. How do you achieve that in Spark and Cassandra, running queries over Spark? Can you do that in Spark?
Well, obviously it's a challenge. One of the advantages of the way that we've architected it, as I've said, is we've taken out that big chunk of the latency that's associated with moving data around. I mean, we have a customer that we're working with at the moment who's working towards achieving that. So, yeah, I'm not in a position to give much in the way of detail at the moment. But those are the sort of targets that we're being given to work against.
Fantastic.
And obviously, it depends on the use. As usually is the answer with Cassandra and this kind of technology, the answer is it depends. So it depends on the use case, it depends on the volumes of data, it depends how distant those components of that architecture are, and how long it takes for the information to be moved around. But those are the very aggressive SLAs that they've been asked to work to.
Thanks.
Okay. I think if that's it, then well, thank you very much, everybody. Thanks for your time, and I hope that was instructional.